Hi, everyone. Here's a quick introduction to Chapter 7, Linear Regression. Let's take a few notes here. So Chapter 7 is all about least squares regression lines. And I'll explain that phrase in a few minutes. But first, let's talk about the goal. And so in the last chapter, you learned about scatter plots. And so you have a bunch of dots, and you learned how to describe it. You learned about describing the strength and the form and so forth. So now we're going to take this one step further. If you have a linear form, then wouldn't it be nice to actually draw a line that goes through those points and gets to as close to as many of those points as possible? That line is called a least squares regression line. Sometimes it's also just called a regression line, or you can abbreviate it LSRL if you want. Also, sometimes it's informally known as a best fit line. Okay, so how do you do that? How do you figure out the line that gets to as close as many points as possible? Because, if you think about it, what is the best line? I mean, there's a line that gets through the points. Here's another line that gets through the points, and here's another one. So, there's a bunch of lines that could plausibly be used for a best fit line, but it turns out there is one best line. And so to start this lesson, the author starts with a nice example of a scatter plot of roller coasters. We have 668 roller coasters in the United States, and the explanatory variable is height in feet. The response variable is speed in miles per hour. And so you can see that down here on the left, you have a bunch of roller coasters, quote unquote, the kiddie roller coasters, not very tall. Let's zoom this in a little bit here. We have these roller coasters. They're very short roller coasters, and they're very slow right there. And then as common sense would tell you, as the roller coasters get taller, the speeds get faster. And so up to, some of these, a 400 tall roller coaster, the maximum speed is like 100 miles per hour right there. That'd be going like almost straight down. So the author introduces this example and then talks about some of the concepts here. And then a couple pages later, we actually draw a line. Here we go. So I think this is just a subset of the data. It's not all the data. So the author gets to the point where they draw a line through the data. Now, how do you figure out what is the best fitting line? The answer is related to residuals. So first, let's talk about residuals. The idea of a residual is you take a dot like this dot, which the author says is the Blue Streak roller coaster, whose height is about 70-something feet tall. But the observed or the actual speed of that roller coaster in the book, it says, is 40 miles per hour right there. However, according to the line would predict that the speed would be a little higher, about 45. And so it's a 5 mile per hour difference between the actual versus what the line would predict. And so that brings us to a formula, which is right here. Residual equals observed value minus predicted value. All right, let's write that down for notes as well. Residual is equal to the observed, excuse me, no, that's right, I'm sorry. I got it mixed up there. It's the observed or actual value. In this case, the actual speed of the roller coaster minus the predicted value, which is what the line would say the speed would be. Okay, now I want to talk about this idea of prediction. One of the main reasons why we do this in the first place, why we spend all this time trying to figure out the best fit line, is for prediction purposes. For example, let's say you build a new roller coaster that's like 120 feet tall. What would you predict would be the actual speed? Well, you can see that the line would say about maybe 55 miles per hour. Right there would be the predicted speed. And so that's what the line is for, so try to make predictions. Now, later in the book, they give you this formula in symbols. So residual is E. We can't use R for residual because R is for correlation. So E is for residual, which actually E is for error, actually, equals observed value, which is just the Y coordinate of a point on the data on the scatter plot, minus predicted value, which is Y with a little hat on top. And we say Y hat. All right, and anytime you see a Y with a hat, it means the predicted value of it. Okay, so then the goal here is to minimize the square of all the residuals. Okay, now why square them? The reason is, roughly speaking, half the residuals are positive. Anytime you have a dot above the line, you'll have a positive residual. And roughly half the residuals are negative. Anytime you have a dot below the line, you have negative residuals. And so if you just add them all together, they'll all cancel out. And so you square them all. So for example, if you have, here's a scatter plot, here's a line that goes through, you have that residual, you've got this residual, you got this residual, let's put another dot down there, that residual, and so forth. And so if you call this like E1, E2, E3, etc., you'd have E1 squared. So the first residual squared plus the second residual squared, kind of like you do with standard deviation, you have to square everything to get rid of those negatives, plus the third residual squared, etc., 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 should equal the lowest possible value. So if you can figure out the line that will give you the lowest possible value of all the squared residuals, then you found your least squares regression line. It sounds really complicated, but actually there's some special properties that actually makes it fairly simple to do. But that explains the phrase least squares regression line, because it's a line that has the least squares, or the sum of all the squares. Okay, so let's talk about properties. So in the textbook, you can skip the next couple pages. The author converts everything to z-scores, which is kind of fun and interesting to do. And there's some interesting properties, like if you convert everything to z-scores, least squares regression line will go to the point 0, 0. And the slope is r. It's interesting, but it's not that useful because we want to deal with real data. But you can skip that page 175. You can skip that page, and we're going to go straight to this part, the regression line in real units, right here. All right, and so the author gives us this formula. Y hat, let me zoom in a little bit here if I can. Here we go. Y hat equals B subscript 0 plus B subscript 1 times X. So first of all, the subscripts are just labels. And I've seen other statistics books, they'll use other letters like A plus BX or MX plus B, but in our book and in most statistics books, they use B sub 0 and B sub 1. And it turns out that B sub 1 is the slope of the line, and B sub 0 is the y-intercept of the line. Okay, so let's back up. Let's write this down for the notes here. So the equation, the equation of the least squares regression line is y with a hat. You have to put the hat on top to indicate it's just a way to make a prediction of what that response variable's value would be. is equal to b subscript 0 plus b subscript 1 times x. All right. Now let's break this down here. So b subscript, actually let's start with b subscript 1 right there. So b subscript 1, that is the slope of the least squares regression line. We talked about slope in an earlier video, but slope is just telling you how fast the line is rising or falling if it's a negative slope. And here's the basic idea. If r equals 1, now r never equals 1, but if it were to equal 1, then it turns out that the slope of a least squares regression line, if you go up 1 standard deviation in the x direction, I'll say sx for standard deviation of the x, then you go up 1 standard deviation in the y direction. And so back to our roller coasters. I think on the next page they have the roller coasters. All right, well, the next page actually has the formulas, which I'm explaining to you right now. But let's go back to the graph of with the roller coasters with the line through it. Just a second here. All right, here we go. Okay, so you can see that if the height goes up like 100 feet, then the speed will increase by about 30 miles per hour or so. So if you take all your data and you calculated the standard deviations of the heights and the speeds, then it turns out if you go up 1 standard deviation in the heights, then you roughly will go up 1 standard deviation in the speeds right there. That's if you have a perfect line. Okay, but of course r does not equal 1. So when r equals anything else, so if r equals anything else, then the slope turns out to be, if you go forward 1 standard deviation in the x direction, then you go up r times the standard deviation in the y direction. So r, remember, is always less than 1. So it's like the slope regresses. The slope is a little bit less than 1 standard deviation in the y direction. And that's, I think that's where the word regression is coming from that idea that the slope is regressing a little bit. So that brings us to the equation for slope. So slope of the line turns out to be r, which is your correlation, which you know how to compute from last chapter, times the standard deviation of y, whatever the y coordinates are, divided by the standard deviation of the x, whatever that is. All right, and once you have your slope of your line, you know how fast that line is increasing. All right, and then so that's the first thing. Okay, and then the second thing is, it turns out that the least squares regression line always goes through the point x bar y bar. All right, which actually makes sense if you think about it. If you have the mean heights and the mean speed, if you want your least squares regression line to go through the middle, then it seems logical that it would go through the mean of both. And it turns out that it actually does. And so that gives you a way to figure out the intercept. If you take this little equation, y hat equals b sub 0 plus b1 times x. If you replace y hat with y bar temporarily, and you replace the b1 with, well, let's just leave it b1 for now. Replace x with x bar. A little algebra, the opposite of plus is minus. So y bar, whatever that is, minus b times the x bar has to equal b0, which is, b0 is the intercept. And so b0, which is the y-intercept, is equal to y bar minus bx bar. Okay, so that's here, let me put a box around the main things you have to know. Okay, so you compute your slope